Sorry, we're already a bit behind then, but thanks everyone for coming. So we're going to have some fun today because I'm going to talk about one of my favorite things in the world, and that is my pedalboard. So for those of you wondering what a pedalboard is, it's a series of devices. There's a picture of it here. A series of devices or pedals that my guitar is running through, and each of them is changing the sound of the guitar in some way. So I thought it would be a fun idea for a talk if I went and created some of these effect sounds in Scala. So before we start, I want everyone to just get acquainted. So we'll go through and introduce you to everyone. So we'll go from right to left because that's the order of the signal chain. So on the right, I'm starting with the AMT little loudmouth. It's been on my pedalboard the longest, and yeah, I bought it around 10 years ago while I was at university. And the fact that I can say the words 10 years ago and at university in the same sentence is kind of terrifying to me nowadays. But it's a volume pedal. So what that means is I can be playing. I'm going to turn that off. And then I kind of come back on it a bit, and then it's quieter. Can you hear that? I'm going to give you a second to all pick your jaws up off the floor for how amazing that effect is. So, yes, it's not very exciting on its own, but what's nice about it, thank you very much. What's nice about having a volume pedal is it's got this little rocker, so I can kind of control it in real time. So that allows me to do stuff like this. And it takes this like twangy instrument that is the guitar and kind of mellows it in a sense where you could use it in a place where it wouldn't feel out of place, where you would want like a string quartet or something like that. So that's that one. I get very sad when I can't have a volume pedal. Next up is a TC Electronic Polytune. This is a tuner pedal, and when I kind of engage it, it cuts my signal, which means it was voted Pedal of the Year every year by every neighbor that I've ever had. But that's not why it's on the board. The reason it's on the board is what you can't see is when it's on, there's a little display here, and it tells me whether my strings are in tune or not, which is very useful. It's very clever, so we're not going to build one of those today. So I'm going to go straight on to the next one. This is the Wamplatumnus. It's an overdrive pedal. So the guitar usually sounds quite polite. And then when I kick this on, it's that kind of angry rock sound, kind of the... And it took out the presentation somehow. So I'm going to continue until we figure out what's gone on there. Anyway, there we go. Right, okay, what was I saying? Yeah, so it's that rock sound, although you hear it in pretty much every genre of music. I have very self-indulgent at the moment. I have 2 overdrive pedals on my board. Second is the PG-14 from JHS, and that's a much different sound. That's a kind of... It's absolutely glorious, and I love it to bits. But that's not, we're not going to talk about that one today. Next one is the ACS-1 from Walrus Audio. This is an amp and speaker simulation pedal. The reason for this is you all know what an electric guitar sounds like. You have this idea in your head of what an electric guitar sounds like, and it sounds good. And that's an electric guitar going through an electric guitar amplifier. And the problem is that electric guitar amplifiers are very heavy, but you kind of have to have them because when a guitar is running straight into the sound system like I'm doing now, they on the whole don't sound very good. But this wonderful little pedal, which is quite a new invention, or they got good recently, lets me sound like I'm going through an electric guitar amp without the medical bills, which is fantastic. And finally, I have the Strymon Cloudburst. And I love this pedal to bits as well. That's going to be a recurring theme. This is a reverb pedal, and it's kind of been on the whole time. Can I have the sound a little bit up? Anyway, so you might not have noticed this on, but you probably noticed when I turn it off. So it sounds a little bit flatter, and then I click it on, it sounds in like a slightly larger room or a small cave or something. It's not much, but it makes me very happy. So now we're all acquainted, I think we'll talk about making some pedals, which is what you all came here for, I assume. In order to do that, we're going to have to talk about what sound is and how it looks by the time that it gets to my computer. So you may remember from school physics that sound is just vibrations in the air. My guitar here has got these two things called pickups, which is taking those vibrations in the air and turning them into electrical current. Now here's a simplified version of what that looks like. And it's an alternating current because it basically fluctuates as the strings vibrate. And so those of you who did high school physics will also remember that the height of this wave basically corresponds to how loud it is. And that's true as well for the voltage. So the voltage is on the y-axis, time on the x-axis, where the height of this wave is basically corresponds to how loud it is. But computers can't really deal with this kind of analog signal, which means that by the time it gets, I've got this little box at the end of my pedal board here, which is sampling the signal at a constant rate. At the moment, it's going about 4,100 samples a second. So by the time it goes to the computer, it looks a lot more like this. And you can kind of see this, you don't lose a whole lot. You can kind of tell what it looks like. And obviously, the more samples you have, the more accurate that's going to be. And yeah, so the thing to take away from this is to the computer, the audio signal is just a stream of numbers. And in this case, I'm using floats. And when you use floats, it's very normal to normalize your values or the magnitude of your values between 0 and 1. So 1 being the loudest that the audio interface can really deal with, and 0 being 0. I've done that again. Oh. Okay, right. So the thing to take away from this slide is audio stream is a stream of floats between -1 and 1. So how might we go around processing this? Bearing in mind, it could be an infinite stream, at least if I carry on playing forever and no one kicks me out of the venue. So a direct approach is something like this. And this is something you might have seen if you've done kind of file I/O before. You have some kind of library that gives you the input stream and the output stream, or access to the input stream and the output stream. And then you allocate some memory in a buffer. And in a while loop, you'll kind of read stuff from the input buffer into your buffer and transform it in some way and then write it to the output buffer. This has a couple of issues. So chief among them is that these reads and writes are blocking. So if I'm doing this within a while loop, it's going to block the thread during the read and the write, which is not super efficient. Lots of audio libraries now allow you to use callback functions, but in my experience, they're really kind of annoying to work with. And that's another thing that comes with here. It's not necessarily, it doesn't look super nice, and it's not super nice to work with. So I figured, how might I make this a bit nicer? And I turned to probably my favorite Scala library, which is FS2. Now, if you don't know what FS2 is, or you missed Zainab's workshops on FS2, or any of the talks that were on FS2 over the past couple of days, FS2 is a functional streaming library for Scala. It makes things, it makes dealing with streams very nice indeed. And we're going to need a few core concepts from the library, so I'll walk you through those really quick. So the first one is a stream. It's got two type parameters. The first being an effect type, which I'll come back to. Second is self-explanatory. It's an element. It's what's in your stream. Is it a stream of floats? Is it a stream of strings? But the first one is an effect type, which is nice because in FS2, streams can evaluate effects, which is super handy if you want to, I don't know, read from an external interface, or if you want to just do some setup or some teardown when you're processing. It's really helpful. Second concept we need is that of a chunk. Processing streams one element at a time is really not very efficient. And that's why when we were doing the while loop, we had a buffer so we could do a bunch at the same time. And same's true in FS2. They instead of processing one at a time, you process chunks. But the nice thing about FS2 is it's usually completely hidden from you, and the library just takes care of it. I'd been using FS2 in production for quite a while before I'd ever touched the chunks directly. But we are going to talk about that a bit. And the last thing we need is a pipe. So pipe is just a function from one stream to another. I guess it's because you can imagine like a stream of things going into a pipe and then they come out looking a bit different. And that might mean that you've processed each element individually and transform it into something else, but it might be something more complicated than that, which we'll see some examples of. So now we have the core concepts. We can talk about what we need. So we need some kind of audio interface, which is going to have an input and an output. The input's going to be an audio stream, like I said. And we said an audio stream is a stream of floats. So that's what it is. It's a stream of floats. And the output is going to be something that takes our stream of floats and performs some effects and plays it out the output, but doesn't emit anything. So this is a pipe from float to nothing. Other streaming libraries have this concept of a sync. This is what a sync looks like in FS2. And while we've set this up, you get this really nice nice description of a pedal, because a pedal, we said, was something that takes an audio signal, turns it into another audio signal. That's taking a stream of floats, turning it into another stream of floats. So it's just a pipe from float to float. I'll talk incredibly quickly about how you might implement an audio interface here. I won't spend too much time on it. I've omitted a lot of the setup, but here you need an audio processing library. We're using port audio, which is a C library, using the SN bindgen. Everyone say thank you, Anton. Okay, don't. Well, thank you, Anton, for the SN bindgen. It makes this very simple. But yeah, if you're going to define a stream from scratch in FS2, what you basically need to do is define what it means to pull a chunk of data from that stream. So that's what we've done here. You said that when we pull, we do exactly the same as we did in the for loop. We get some kind of buffer and we read information from the buffer. We output that buffer as a chunk. If you're sitting here thinking this is very inefficient because you have to allocate memory each time instead of reusing it, boy, are you going to hate the last section of the talk. But that's a good thing to make sure is understood. If you're doing, it's really fun to do it this way, and it gives you nice representations of stuff. But if you're doing audio processing, usually you have limited hardware. This is not a good way of doing it because you need tight control over your memory, tight control over your CPU usage. Anyway, that's how you do the input, and the output's just the same. You split it back up into chunks, and then you write it to the output stream. And because we now have a full blocking thread in the pre-release of Cat's Effect for Scala Native, we can do these things without worrying about blocking threads for our main stuff. So this gives us this really nice way of plugging these things together to make an app. So I get my audio interface, and then I run the input through some pedals, which are just pipes, and through the output, and then I just compile that and drain it. And at the moment, I have a version of this running where there's no pedals, so that's what you're hearing me. That's how you're hearing me play through the sound at the moment. But we want to make it a bit more interesting, and I promised you all some pedals, so let's finally get to that. So we can start with volume. I briefly mentioned that if we go back to our representation of or our graph of the signal, that the height of the wave governs how loud the signal is. So if we want to make it quieter or louder, we just need to make it, to make it quieter, we need to shrink it. To make it louder, we need to make it bigger. And you can do this pretty easily. So you can just multiply by a constant and make it smaller. This constant is called the gain. That's an audio processing term. If you hear guitarists talk about gain in guitar pedals, they probably mean something slightly different, which I'll talk about a bit later. But it's defined as the ratio between the input volume and the output volume. And I showed you earlier that I was kind of sweeping it with this control. You can do a similar thing. You just need a stream to change the gain that is sampled at the same rate as your audio signal. And then you can just multiply those pointwise together. That's a volume pedal. We established it wasn't super interesting. So let's talk about overdrive. So some guitar history for you all. I'm going to go back again to our reference image. Audio signal looks like this. And I kind of briefly alluded to the fact that my audio interface has like a maximum volume that it can really deal with. And it turns out guitar amplifiers are the same. There's like a maximum volume they can amplify stuff to. And in the 50s and 60s, it became really popular for people to be turning their guitar amps up as loud as possible, far past what they were supposed to be able to deal with. And they can't deal with it anymore. And what kind of happens is the wave kind of starts to squash itself so that it still fits in the thing. And it sounded really, really damn cool. And so everyone was doing it all the time. And there's a problem here, which is, one, if you're running your amplifier about to explode all the time, it doesn't have as long a shelf life as it was if you're using it properly. But that kind of pales in comparison to the problem that your audience has to listen to your music being played at full volume all the time. So in order to save everyone's eardrums, in the 60s, I guess, people were setting out to make pedals that would do the same thing at a lower volume. Now, you can achieve this effect with transistors, which will overload in the same way as the guitar amp, but at a lower volume. And they'll kind of still do this rounding. This is what we call soft clipping, because it's rounded. But you can also take diodes and just kind of chop off the top and bottom of the wave. And that's called hard clipping. And it's a similar sound, but very different. If you look in the repo, you'll see examples of both soft clipping and hard clipping. But I'll talk about hard clipping because it's very easy for us to implement right now. So this is what we call symmetric hard clipping, because we're clipping both the top and the bottom. But it's very easy for us because we said we've got some kind of threshold, and if it's above that threshold, we just want to bring it down to that threshold. And likewise, when it's below the other threshold, bring it up to that threshold. So we can implement symmetric hard clipping just with this function here, just using the math max and min. But I didn't want to stop there. See, I told you I brought the Wampler Tumless as my overdrive today. That's because I wanted to talk about, because it's based on a very famous pedal in guitar history called the Klon Centaur. Now, this has a bit of an infamous history. Essentially, sometime in the 90s, there was an audio engineer called Bill Finnegan. He was not happy with the overdrive pedals that were on the market. He wanted something a bit different. So he's trying out things, he's working, and he comes up with something he likes, and he decides he wants to sell it. Now, he doesn't want other people to know what his circuit looks like, because he doesn't want other people to build it. So he sprays a load of like goop all over all the circuit boards so you can't see what the circuit is. And this, coupled with the fact that he was just one guy and struggling to keep up the demand of people ordering all these pedals from him, these become very rare, and the price goes up astronomically, and it's still true. It's still astronomically high today, by the way. This is a listing on Reverb that I found a couple of years ago. Reverb is like eBay for musicians. Someone's selling a Klon Centaur for 8,000 euros. My favorite thing about this slide, by the way, is in the bottom right-hand corner, there's a little sign that says, "Need help?" And I kind of feel like if you're about to spend 8,000 euros on a pedal, then you probably do. But that's not why I'm going to talk about it. As you can see in this picture, on the left-hand side, there's this knob labeled gain. Now, despite what I told you earlier, this knob doesn't just make the sound louder. It does do that. There are a couple of diodes at the back of the signal chain that are clipping off the wave. And this knob does make the sound louder, and then that means that it's going to hit the clipping stage earlier, so you get more clipping, you get that more distorted sound. But what's interesting and kind of unique about the Klon style circuit, by the way, we do know what the circuit looks like now, because a couple of people on a forum pulled their money together, bought one, and took it apart. So this is why I'm able to talk to you about the circuit now. But yeah, what's kind of unique about the the clon is you're almost always hearing two signals when you're playing through a clon. You're hearing your clean signal, so the one that's not clipped, and you're hearing the clip signal, and you're hearing those at the same time. And this knob on the left kind of also acts as a sort of blend. So if you're all the way to the left, you're just hearing your clean signal. And as you turn it to the right, you hear more and more of that clip signal blended in. And I thought it would be fun to try and do something like this. So I'm kind of thinking something like this. So my input goes in, and it goes down the bottom when it gets clipped, and I bring down the volume a bit, which I'll call like a blend control. And then I also pass through my clean signal, and I decrease it by a factor that's related to the blend. Here I've put 1 minus B, but in reality you probably want this, you probably want this lower one to have a higher gain factor, because when you clip off the waveform, it's going to get quieter. You probably want to compensate for that a bit. But we run into a problem because we don't yet know how to run two pedals in parallel. And I was thinking, okay, so what do I need to do? I need to be able to split my signal. I need to be able to run it through two separate things. And I need to be able to join it back together. Now, joining it back together is super easy. It turns out if you are playing two audio signals at the same time, the effect is exactly the same as if you just add all of the values together. So I've defined a semigroup on the streams of floats, which importantly is not the semigroup that comes out of the box in FS2, because that's about concatenation, but we don't care about that. When we combine streams together, we want to add them. So you can just define this semigroup that adds the streams together pointwise. Now, the next thing we need to do is to split our signal, which is a little bit more complicated. And I was thinking, okay, if I was doing this with a message stream in production, how would I do this? How would I split the signal? And I guess I would just put some messages on some kind of topic, and then people could subscribe to this, and then they'd all have their own copy of this stream. And you can do this. FS2 has a topic concurrency primitive. So here it says unthrottled chunk topic. That's just because it's a very small wrapper around FS2's topic. The difference is I'm publishing chunks one at a time instead of elements one at a time. And the unthrottled part refers to the fact that I never stop you from publishing to the topic, even if the downstream consumers haven't finished processing their messages yet. And then you can do this. You can just straight up translate this diagram into Scala. So you have the topic, and you subscribe once, and you put it through one pedal. You subscribe a second time, you put it through the other pedal, and then the result stream that you want is what happens when you combine these two outputs together using the semigroup. And then concurrently, you just want to publish your input stream through that topic. And that means that this thing that I showed earlier, it's pretty easy to implement. It just looks like this. I'll show you very quickly what that sounds like. So I'm going to turn off my overdrive and everything and just run it through the Scala version. To be honest, like when I coded that and I kind of looked at it, I was like, there's no way this is going to sound good. But to be honest, like after hearing it, you know, if I had no other option, I would gig with that. Like that's, I was really surprised. And I was also surprised by the next one that I tried, which was reverb. So this is the pedal we talked about that makes you sound like you're in a cave or a bigger room, something like that. I found this reverb algorithm on the internet. It comes from a paper in the 60s by a guy called M.R. Schroeder, or Mr. Schroeder, I guess. I actually found this through a blog post on Medium by a guy called Rishi Dow. There's a link to that in the repo if you go there. It's a really cool blog post, goes into this, explains it more than I am about to. But yeah, basically Schroeder in the 60s developed this algorithm, and it looks like this, which looks really, really damn complicated, but don't worry, we're going to break it down. So you can see these sections, like everything on the left, there are 4 kind of things that look similar going in parallel, and then there's 2 things going in series afterwards, and the rest of it is just stuff that we already know how to do. And the things on the left I'm going to call an echo stage. The reason is Schroeder thinks, okay, if I'm in a cave and I shout, like I shout echo, you know the effect, and you say echo, and you hear echo, echo, echo. Gradually, it will repeat after a certain amount of time, and it will get quieter. And the way he solves this, he just builds this. Okay, so this is the repeats. The stream goes in, it gets delayed by, I don't know, a second or whatever the time is, and then it splits. That signal goes directly to the output, but it also gets multiplied by a factor to make it quieter and then fed back through that delay. And you get this kind of thing going. When you look at the impulse response, that you get this loud sound, and then it gradually kind of fades away, which, yeah, you get the impression. And that's a guitar effect in itself. If you listen to a lot of U2, you'll hear a lot of echo instead of reverb. And we can make one of these fairly easily. The thing is, we already know how to add this signal together. We already know how to split our signal. What we don't know how to do that yet is this little delay and delaying the signal. Now, if I'm doing this in the traditional way, if I want to delay the signal, I have to write it somewhere in a buffer. I have to remember to come back to it in a second's time and play it. When I'm using FS2, I don't need to do any of that, which is quite nice. If I want to delay something by a second, I'll just prepend a second of silence onto the front of it. So you get this really basic implementation of the delay line. Again, it's not efficient memory-wise, but it sure looks nice. And so now we can use this and we can translate our diagram. It looks like this. I've got the topic highlighted here. You bring that up. You've got subscribing once, which is going directly to the output, and you're subscribing again, which is getting made quieter, and the output is that output stream I just mentioned, but concurrently you want to add together the input stream with the feedback stream and run it through a delay line and then publish it through your topic. So, back to the diagram. Here's the problem with just using the echo stages. It doesn't sound very natural, because actually when you're shouting in a cave, you don't just hear your voice bouncing off one thing. You hear it bouncing off like 100 different things at the same time. And so really what you should have is, I don't know, hundreds of these things just in parallel. So that to count for the different like delay times, different gain factors as they decay. That is not computationally feasible. So Schroeder's kind of solution to this is say, okay, I just have 4 of them. I run 4 of them in parallel, and that's going to generate a bunch of repeats. And then I'm going to run this through these 2 stages here. And these things are going to take those repeats and generate more repeats from those. So he calls this an all-pass stage. And that looks like this, which looks a little more complicated than what we just did until you realize that this is an echo stage. This is just what we just built with a different gain factor. So actually the implementation of this looks super simple. You just run these things in parallel. This is the thing I love about writing audio stuff in this way, is just how goddamn composable everything is. It's just, everything is really neat to combine together. And that continues to when we want to do the full reverb algorithm. So we're going to generate 4 gain stages, 4 echo stages with different gain factors and delays. And they're all in this ratio, which comes from the paper. I don't know where it comes from, aside from the fact that it comes from the paper, but it sounds good. And then there's also this function for working out what gain that should have based on your delay. Again, I don't know where that comes from, other than it comes from the paper, but it works. And then, yeah, you just translate that diagram into Scala, and you get something like that. I'll do a quick demo of that. Again, my reverb pedal is off. And again, that was something I kind of put that down, and I was like, yeah, there's no way that was going to sound good. And genuinely, like, not even the case with the overdrive like last time, where I was like, yeah, if I had another choice, like, I would use that. That's pretty usable to me. So yeah, like I had a lot of fun writing all of this stuff, and it was like pretty rewarding. I hope you have fun too listening to the talk. But that's all I've got, and I think we still have time for some questions, even though we started a bit late.
Thank you. Wow, this is amazing. I'm so happy because I saw the mention of that on one of the German meetups, and I was really hoping to see that live. So it's fantastic. My question is, if you run this for long enough, do the various artifacts of garbage collected runtime, do they get in the way? Because timing is like super important here, right?
Yeah, so it depends on how complicated these things are. I can run the dry signal for, I don't know, like I haven't run into problems with the dry signal yet. The reverb one that's doing a lot more resource heavy. On the early release, so I've been keeping a close eye on the Cat's Effect releases for the multi-threading, because there's blocking operations. So if you don't have that, then they get in the way a lot. And at the start, the garbage collector was getting in the way a lot. Like I knew it was the garbage collector because if I turned it off, it was all fine. And now with the latest release, it's pretty good. I would say it still does get in the way a bit if you leave it if I leave the reverb for like a few minutes, it will start getting in the way. But yeah, it's pretty good. I assume it's going to get better.
So how many pedals have you simulated, and what is your next one that you haven't done yet?
So with this approach, you're a little bit limited. I'm a kind of a simple guy, and these are my favorite pedals. These are the ones I like on the board. These are the ones that have been around for the longest. The reason they've been around for the longest is they're very easy to make with electrical components, and we've done similar things as you can do with electrical components here. More of the fancier ones, the pitch shifting ones, are much more complicated. I think if I was going to do that, I would have to get involved with like fast Fourier transforms and stuff. I suspect this is not fast enough to do those kind of things. But recently, I think the most recent one I did, originally I didn't do the soft clipping, so the other form of overdrive. And then I was writing slides for this and trying to plot it on a graph and trying to come up with a function that looked around the same. And the kind of solution I came up with was to take like a normalized distance from the threshold you wanted and square it at first. And then I found it sounded slightly better to my ears if I did it to the power 4 instead. So that was fun. I did do some very rudimentary octave effects. So pitch shifting is in general quite difficult. For octaves, it's quite easy because you're just doubling or halving the length of or doubling the frequency. The problem there is you run into problems with the sample rate. So it's very easy to do the octave down because you can kind of artificially double everything. But no, you're still running into this problem that your input and your output are kind of working on different assumptions. But it is kind of fun, and you can do like a fun low quality voice changer thing. I'm sure I could do a phaser probably. I haven't tried that yet. Yeah. I don't know.
And does the latency add up as you add more pedals, let's say?
Yes, yeah. I mean, it does. Like the performance definitely drops as you do more. As you can see, like the reverb is so much more intense than the others because it's got so much stuff working in parallel. So, as I would say, the latency. Yeah, it depends how you set it up. So you can either set up your input so that you take all of the stuff from an input and put it in a queue, which is what I'm doing. Earlier, before I had it, so it was only taking stuff from the input when it's written to the output, and then you kind of back pressure a little bit, but then you'll get kind of glitches in your audio. But yeah, everything's limited by how quickly you can process things, essentially.
Well, First of all, thank you for an amazing talk. That was really fun. And I actually just wanted to know if there's a repo or something we can have a look at.
Yeah.
Try ourselves.
Sorry, I didn't mean to cut you off. I just had the realization that I didn't go to the next slide. So there's a QR code of the repo there if you want to check it out.
Thank you. Great talk. If I'm not mistaken, the latency should be more or less constant because it's like only the audio latency of your audio interface buffer, right? Because every chunk will basically get processed in one step. Doesn't matter how many stages you add to your pedal board, if I'm not mistaken.
So that's the subtlety of how you set up the input, because we have it going. So if we go back to the oh dear, how do I do this easily? So it's slightly hidden here because I've shown it kind of looks like you only pull from the input stream when you want to read from it. But because we have it concurrently going somewhere else, it's actually just doing it all the time. And so everything that comes through the input is going to get read. And if you don't process it fast enough, it's still in the queue for you to process, essentially.
Right, but as long as your CPU is not maxed out, it's basically just you have the latency of your audio interface.
Oh, sure, as long as you can process everything. Yeah.
And the performance remark for the colleague, because I do a little guitar processing digitally, basically you can have almost infinite pedals nowadays simulated at the same time, and your CPU just laughs at it. It doesn't matter if it gets processed with 44 kilohertz. This is for modern hardware, it's a joke.
What is actually determining the sample rate? Is it the output stage that is dictating the?
Yeah,
like
so
the rate at which it consumes the data?
Yeah, I think my understanding of this, which is not a lot. So when you go to your audio processing library that interfaces with your interface, you set that sample rate. So it says how often to put data in the buffer. And my understanding is that there's just that amount of space in the interface that it can get. And then when it's time to the next one, it will just replace it. And if you didn't get the last one, tough luck, you're out of time. But yeah, it's just like a constant you set based on the interface library.
I think it's the driver, right? Audio interface driver has a sample buffer that you can set. And this would be probably the size of the array that's allocated.
Sure, that sounds about right, yeah.
Okay, last question.
So I'm really curious about your development process because it sounds really cool. Do you just like sit there and play your guitar and then just hear the stuff coming out of your laptop?
Pretty much. This was a really fun project because you get to, usually when you're programming and stuff doesn't work fast enough, you're like, oh yeah, something's not, I've got messages building up or something. But this you can really you can hear the performance of your app by if the app has if the sound has glitches or not. That was really fun. So yeah, it was basically I code a bit and then I play my guitar through it. Compile times are a bit of an awkward thing for that, but whatever. And then there was one bit where I got stuck at an airport for a bit, and the first time I gave this talk, I was traveling back the week before I got stuck at the airport, and I was like, I should work on this talk. But I don't have a guitar with me, so I'm kind of sat in the airport coding and then just kind of making guitar sounds with my mouth into the laptop microphone. So that was quite fun.
Actually, I've got another tiny question off that then. Does that mean that you could probably see this being used for stuff that's not just a guitar?
Do you mean like just basically other audio signals that are, yeah. I mean, there's nothing special about this being a guitar signal. I could have had a microphone plugged into here. I could have, which could have been listening to any instrument, and it would have done the same thing.
Thank you.